So welcome to the webinar today, everyone. My name is Ian Trevoranis. I'll be serving as host and moderator. With us is Mark Buemiller, Vice President from HORIBA Scientific, and Mark is going to be talking to us today about different things you might want to take into account when you're dispersing powders and liquids. The presentation should last about, I don't know, Mark, could you say 40, 45 minutes?
Yeah, say 40.
After which we'll have a few minutes for a Q&A time. Without any further ado, please begin, Mark.
There's a picture here of Mark in Dubai, and just behind one of these palm trees would be the tallest building in the world. I was there for Arab Lab just a couple of weeks ago, and spring was kind of slow coming to Paris. I was very happy to be at Arab Lab, but I'm happy to be here tonight. It's nighttime in Paris as well to talk about dispersing powders and liquids. So I just have to first make sure I understand my controls on my computer. How to go down a slide. Bear with me. So I hit the down button. That didn't do it. I hit that button. That didn't do it. Do I hit enter? So hang on a second, Ian. All of those should have switched me to the next slide.
What about your right arrow button?
Hold on. That changed it. So the right button on my mouse. All right, so as we talk about these powders that we're going to disperse in liquid, powders generally exist in some kind of clumped aggregated state. Just a picture here of powders, and generally you're not always looking at individual particles. They're clumps stuck together, either by weak or strong forces. If we talk about agglomerates and aggregates, there is an agreed-to terminology here. We generally talk about aggregates being clumps or assemblies where the particles are held together by loose forces, and maybe these could be broken apart fairly easy just by energy or reducing surface tension. But aggregates are usually held together by much stronger forces, maybe covalent electron sharing, maybe some kind of stronger chemical bond, and these are actually much more difficult to break apart. What we're usually looking for when we're going to make particle size measurements is a nice well-dispersed sample, because most people want to perform measurements to find the individual particle size state. So we'll be talking about how to move from here down to aggregates and into this well-dispersed state, because we're really talking about dispersing powders prior to making a particle size measurement. And I have to get rid of this. So I thought since I had my mouse today, I could get rid of having that box show up. It does show up, right, Ian? So let me get rid of drawing tools. Go back to here. And so Ian, remind me how to get rid of the drawing tools box. I just click on it. Sorry, there we go. So what we're going to talk about is how we're going to disperse these powders. We could measure powders in a dry powder feeder. Then the dispersion would be just a question of how much energy do we put into the system using the dry powder feeder. But if you want to suspend the powder in a liquid to do the measurement, that's the topic tonight that we'll be discussing. We have to choose the liquid we're going to disperse it in, and certainly we want to avoid dissolution. If the powder doesn't naturally wet, we might have to add a surfactant. We may need to add another chemical to avoid re-agglomeration, dispersing aids, or we might just need to add a little energy to break up those loosely held aggregates. So we're going to talk about the strategy of how to make these decisions prior to making that measurement. So one of the first things we can do is just, if we think we know what liquid we want to work with, and typically it's water, you can look at a picture here. We can just put some water in a beaker, throw some of the powder on top, and see if it floats on the surface, such as we're seeing here on the left. Then we'll say that that is not wetting. Or if it readily starts sedimenting down to the bottom, either because they're large and heavy or because they're wetting very easily, then we're in luck, and we have found the proper liquid to use for the dispersion for taking the measurements. So that's what we usually do, is just a quick check for wettability. But we might discuss kind of what's going on in terms of the surface chemistry of wettability, and that's what we'll look at in these next couple of slides. And when we define particle wetting, we usually talk about the contact angle. So contact angle kind of tells us, if we take a drop of maybe water and put it on top of a surface, what is the shape of that drop? And we could model that using the Young equation. And with the Young equation, this contact angle is actually the boundary condition. Or we could just observe it. Down here I show a water drop on top of a cloth which has been treated, so it's highly hydrophobic. But usually if we want to have good wetting, what we want to have are small contact angles. And what we're often doing when we're preparing a powder sample for measurement is we're looking for ways to reduce that contact angle to make it more hydrophilic so that it will disperse readily in the solvent we've chosen. So we can talk about contact angle. We can also talk about surface tension. So if we think of the water droplet on a glass surface, maybe that has a very different surface tension than if it's on the cloth we showed you on the previous slide. So if we think about surface tension, if we think of like water on glass, maybe that's around 30, and if we talk about more hydrophobic surfaces, it might be around 70 millinewtons per meter. When we talk about an area per square area, then we're actually talking about surface energy as opposed to surface tension, but we'll call that roughly the same thing. So if we look at the water drop on a surface, and we're up here at a high value of 70 and would like to reduce that, what we might do is add a surfactant to the situation to reduce that surface tension. And we'll remind you that a surfactant is a molecule that has two components. It's usually a hydrophilic head, which is polar, and the hydrophobic tail, which is usually hydrocarbon chains, which is nonpolar. So if we add a surfactant to this mixture, where it's just a liquid-solid interface, what we usually see is a slight decrease as we start adding the surfactant. Then there's a linear region where it decreases, and eventually this surface tension levels off. And when that surface tension levels off is usually where we have reached the critical micelle concentration. So what happens are when we reach a certain concentration, and sometimes we need to add some energy, these molecules start self-assembling into micelles. And when we self-assemble into micelles, they're assembling themselves and they're no longer treating the surface. So this is just how we can use surfactants to reduce surface tension. It also reduces that contact angle, and that's what prepares the powder to be better wetted for measurement in our particle size analyzer. So here's a particle, and before it's treated it might have a very large contact angle with relationship to the liquid we're going to disperse it in. The goal is to reduce that contact angle to improve the wetting, and ideally we coat the entire surface of the particle with the liquid, maybe it's water that it's dispersed in, and what we're going to do is add the proper concentration in order to completely coat the surface of that particle. The concentration is very important, actually. As we add the surfactant, it's going to behave a little differently in the system. Here we're plotting mean particle size versus surfactant concentration. And when we start adding the surfactant, we start seeing the mean particle size decrease just because we're probably taking those loosely held aggregates and dispersing them to the single particle state. Then at some point at this concentration, we've reached the lowest possible particle size without having already added more energy. And this is the concentration we want to use for dispersing this powder in liquid. But if we keep adding too much surfactant, then we typically will see the particle size increasing again. This perfect concentration range is usually very low, maybe like 0.01%, but what we want to do is make sure that we don't get to the point where we start seeing re-agglomeration, which occurs when we have too high of a surfactant concentration. And to explain how that happens, just look at the interaction of the surfactant molecules with the surface of the particle. So in the ideal situation, what we're doing is we're coating the surface of these particles, and the surfactant molecules have coated this so that this particle is now very happy in the liquid medium that we're dispersing in. But if we keep adding more and more surfactants, what can happen is the particle surfaces are coated, and now there's an excess of surfactant molecules, and they'll start stripping off of the surface and start forming these micelles. So this means we're up here at that critical micelle concentration. And when we start stripping surfactant molecules off of the surface of the particle, then we have uncoated surface, and then either the particle might want to phase separate somehow on us, or we could start seeing re-agglomeration. That's what we're trying to avoid. And that's when you start seeing that increase again in the particle size distribution. So just to summarize the effect of surfactant concentration, before we add surfactant, the particles might just be agglomerated on top of the liquid. We find that optimum condition where the particles are coated and well dispersed, but we must avoid that excess surfactant concentration where we see re-agglomeration. Now, I wish there were a theoretical way to know what these concentrations are. I gave you kind of a range of 0.01 to 0.1%, but typically these are experiments we must do in our laboratory and with the use of the particle size analyzer to make sure this is optimized. Let's look a little more closely at surfactants because we need to choose which surfactant might we use for a given powder-liquid mix. These are just some pictures again of surfactants where we have the hydrophilic head and the hydrophobic tail. The tail is usually some kind of a hydrocarbon chain and the head is typically polar. And there's a range of surfactants we could use that we usually break down into the categories of non-ionic, where there's no charge on the head group, anionic, where there's a negative charge, cationic, where there's a positive charge, and the zwitterionic, where we actually have both positive and negative charges on the head group. So if we understand our powder properties and the liquid we're working with, this may help us choose which surfactant would be most appropriate for the sample that we're trying to measure. I'm just going to give you some examples of what some of these surfactants look like. Most typically we use non-ionic surfactants. I'll explain why in a few slides. So this is just the molecular structure of IGPAL. And I should remember it's IGPAL CA630, I think, is the actual name of what you would go search for. Tritenex 100 we use a lot. If we need to use an anionic surfactant, I think the most common one we use is aerosol OT, although it's a solid and you have to prepare this in advance. You don't just reach for aerosol OT and use it 2 minutes later. And for cationic, trimethyl hexadecyl ammonium chloride is just one of the examples I found where maybe we'd want to use a cationic surfactant. We use cationic surfactants frequently for organic molecules. So here are some of the surfactants we keep in our laboratory, both here in France, where I am, and in California, where Tori is. And if we know nothing about the system, we most typically first reach for the non-ionic surfactants because they'll adsorb onto both charged and neutral surfaces. So usually the IGPAL and the Tritenex 100 are the surfactants we first reach for. Tween 20 is another potential non-ionic surfactant. Aerosol OT if we want to reach for an anionic, and we don't use cationic all that often, but again, if you're dealing with biological samples, that might be a group of surfactants you would need to keep in your laboratory as well. So remember, this is what we're trying to do. So here is a particle, and it's not very happy in water. So what we want to do is have the hydrophobic chain attached to the surface of the particle, exposing the hydrophilic heads. And the hydrophilic heads are then happy in water, and this wets and it's easier to perform the particle size measurement. So there's a little advice in terms of surfactants, what they are, and how we might choose them for our kinds of samples. Maybe I should have already said, well, you do have to first figure out what solvent we're going to use. We typically hope we can work in water. But don't forget, sometimes other liquids might work better. You know, if you're having trouble dispersing a sample, it's not so hard to just reach for alcohol, IPA, or ethyl alcohol. And there are other times where you need to reach for that hexane or something like that. We just try to avoid it just because of handling issues. But there are times where you're going to need to use organic solvents also, and you might need to consider that when choosing the best solvent. This is actually a slide I got from Ian. He was doing a search probably for a customer not so long ago, and they're saying, okay, can you disperse this lead powder for us? And Ian did what most of us do now. We go into Google and you type in a phrase that might make sense, like lead particle suspension. And he just came across an article somewhere that says, yeah, well, we dispersed ours in MEK. So this is kind of how we search for refractive index and for other things these days, and it's just often how we find information, including ways that we might choose liquid we should use for dispersing our particles. If there are several candidate liquids, or candidate surfactants or concentrations. It's a good idea, even if you aren't meticulous with your creation of the samples, get some clear glass bottles. Disperse it in different liquids or in different concentrations of surfactants. Shake them and look at them. And you know, this is how we do a lot of work with what's working and what isn't working is just the use of the naked eye. So don't be afraid to do this and to, I'll just say, tinker in your lab to look at what's the effect of putting this in different liquids, or if I'm going to use a surfactant, what looks like the better concentrations. There's nothing wrong with some trial and error when going through these kinds of experiments, although if we want to take a more rigorous approach, probably the best documented rigorous approach is ISO 14887. This tells us an approach we can use if we understand the powder and the liquid we're going to put it in, and some ionic strength and some other things about our system. So this generally thinks that you're probably a chemist in a chemical company, and this is a material you're used to working with because you have to mill it or do other things with it. And if you really understand your system, then you can take a more rigorous approach as opposed to the tinkering in the lab approach we talked about on the last slide. So I'll take a few slides here to go through the procedure, which is outlined in this ISO document. So the first thing we want to do, and I just put up here when tables come from the ISO document to give it proper credit. And I don't show all the tables because that's inappropriate. If you need an ISO standard, you have to go buy them. And I'm a little sensitive to this because I'm on the ISO committee TC24 that writes all the standards for particle size measurements. And you know, even when you work on the committees, you don't get to have free copies of the standards you created. So it's the only way that really ISO exists is through selling the standards. So anyway, that's why I don't show the entire tables, but just kind of the feel of it in the presentation tonight. So first of all, you have to say, okay, what is my powder? And we're going to take powders and we're going to put them into these classifications. Is it a metal, metal oxide, ionic salt, etc., or a weakly polar solid? This is the way the table looks in the ISO document, and you can actually look up, well, I'm dealing with calcium carbonate, and it will put that into the category of ionic salt. So over here, I just kind of turn this around and say, so what are some common examples of metal? Think of aluminum, but a metal oxide is aluminum oxide. So we'll need to put our powder into one of these categories in order to be able to use the approach outlined in this ISO standard. Next, we're going to choose our liquid. We probably start with water, but you know, as you look at the ISO standard, it's going to call acetone highly polar, whereas cyclohexanone is only polar. So it's helpful to know how this is categorized. I'm not sure this is the language we all use, or that we'd call isooctane nonpolar. But we need to have a table to categorize the liquids we might consider using. And then there's a long list of dispersants, and I've described surfactants, but dispersants could include surfactants and other chemicals, which in particle size we would usually call admixtures. So we'll discuss dispersants in a little more detail later on, but there's a list of dispersants and it starts categorizing these dispersants. So if we think of pluronic, you know, that's a copolymer, or if you think of lecithin, you know, lecithin is used a lot in the pharmaceutical and food industry because it's actually an edible surfactant. I think it's made from soybean oil, and it's a zwitterionic surfactant. So we have to understand our surfactant and dispersant list fairly well. And if I have all this information, then there's a table provided in the standard which kind of pulls all this together, which says, for instance, if you're working with a metal oxide and you're going to disperse it in water, first of all, you want to know something about the ionic strength. And in a few slides, I'll talk about the ionic strength can actually help you choose should you use steric or electrostatic stabilization. But if I understand the ionic strength, then I'll say, well, first of all, make sure that you avoid the isoelectric point. So this is saying make sure with metal oxides you avoid the pH where the zeta potential is 0. Make sure you're several pH values away from the isoelectric point, which we will define later as well. So in this rigorous approach, if I'm working with carbon and I'm going to dissolve it in water, I might use one of these dispersants. So kind of this is the way this particular standard will work if you have it in your library. Categorize the powder, understand your liquid, understand the dispersants, and then there's a reference table which will suggest perhaps the better way to approach to dispersing this powder in liquid. It's a very valuable document, and certainly we keep it in our laboratories to refer to. So I could kind of summarize it and say, if you're working with ionic salts and you're in a highly polar liquid, then you need to add a copolymer to make sure it disperses correctly. Whereas if I'm dealing with a metal oxide in water, just make sure you look at your pH and avoid the isoelectric point. So we'll talk about electrostatic versus steric stabilization, but in general, my personal experience is I generally take the approach of electrostatic stabilization and don't really keep block copolymers around in my lab when I'm just doing particle size measurements. So to understand dispersants and Zeta Potential and these other terms, we'll have to talk about particle interactions a little bit. So I could probably come up with another joke. Two particles meet in the night, and what are the chances of them hooking up together? Well, so two particles here are attracted to each other, and it's usually the van der Waals forces which attract them. But they're also, if there are charges on the surface of the particle, repulsive forces. And the question is, what's going to win here? The attractive forces or the repulsive forces? In real life, maybe we would add alcohol to the situation, and that would change. But we can actually look at these attractive and repulsive forces. And what we're trying to do usually is to avoid this agglomerated state. And what we're going to do is try to build up the charge on the surface so that they never have the chance to get close enough to turn into agglomerated particles. So we can actually model this interaction as a function of distance. So this is potential energy versus distance between the particles. And we can use DLVO theory to model this. So up here we have the repulsive forces. That comes from the electrostatic forces on the surface. We have the attractive forces, which are van der Waals. And what we want to do is take the total energy, which we have to look at the summation of the attractive and the repulsive. And what we want to do is look at what are the chances of overcoming this barrier. We have to know something about the thermal situation. The motion of the particles is important. And if we can make this barrier high enough, then it's unlikely these particles will ever stick together and agglomerate. So what we want to do is increase the repulsive forces to make that barrier high enough these particles will not agglomerate. So this kind of brings us into a quick discussion of dispersion stability. We want to have a stable dispersion, certainly in our instrument. While we're taking the measurements, we don't want things going on with the particles during the measurement. So we want these individual particles. We don't want them to flocculate. We don't want them to aggregate or to settle down during the measurement. So what we want to do is create a stable suspension during the measurement. And there are two classic approaches to dispersion stability. One is electrostatic stabilization, where we build up a charge on the surface, and essentially these particles act like magnets and repel each other. When we typically use electrostatic stabilization, when we know the relative permittivity of the system is greater than 30, and if the ionic strength is less than about 0.1 moles per liter. So ionic strength, well, we really just have to know the concentration of ions and what kind of ions they are. So remember, ionic strength, you just kind of do a summation of the concentration of the ions, but then you take the charge number and that's squared. So the charge number is very important when trying to estimate the ionic strength of your sample. Now, if the dielectric permittivity is down under 30, or the ionic strength is greater than 0.1 moles per liter, then we might go the route of steric stabilization. We're actually going to probably take these block copolymers, adhere them to the surface, and then these particles, due to an exclusion effect, can never actually get close enough to aggregate and then become a problem during the measurement. But most of what we will continue talking about is electrostatic stabilization. Personally, we think that's a little easier for just doing quick size measurements. So when we talk about electrostatic stabilization and trying to increase the charge on the surface, the way we define that charge on the surface of the particle is the Zeta potential. So here's a particle with a negative charge on the surface. Positive ions are attracted to the negatively charged surface. Negative ions are attracted to the positive ions, and we build up this electric double layer. And the zeta potential is defined as the potential measured in millivolts, shown here from 0 up to certain potential measured in millivolts at this distance from the particle surface, which we call at distance the slipping plane. At this distance, the ions within, to the left of this, towards the surface of the particle, these ions move with the particle when it moves. The ions outside of this distance remain randomly dispersed throughout the liquid in the sample. So the zeta potential could be a measurement where we can understand, have we increased the charge on the surface enough that we can avoid the reagglomeration of particles during the measurement. So now that we understand a little something about these particle-particle interactions and what zeta potential is, we can talk about dispersants. So we usually talk about using surfactants as wetting agents, but the ISO standard actually puts surfactants and admixtures, which actually will just put more charge on the surface, and puts them all in this lump category of dispersants. So we usually use surfactants to wet particles, and maybe we'll use some energy, pump speed, or ultrasound to separate the particles. And we, in particle size, usually talk about dispersants as what we will add to build up charge on the surface to keep those particles apart. And the category in the ISO document that we would typically use would be polyionic salts. So sodium hexametaphosphate, sodium tetrapyrophosphate, these are the kind of admixtures or dispersants we will typically use. So when dealing with the most difficult powders, that usually implies they're small powders that we're having trouble dispersing. Instead of doing the measurement in DI water, we'll do the measurement in DI water but at some concentration with sodium hexametaphosphate, and this will actually add charge to the surface to keep the particles from reagglomerating. In the ISO document, there are other dispersants talked about. So, IGPAL, Triton X100. In the ISO document, they actually call that PEO/alcohol dispersants. So surfactants help the situation, admixtures help the situation. This is just showing some of the other information from the ISO document, and the nice thing there is they actually tell you who makes the chemical, so that may be useful if you're not particularly familiar yet with how to go find tween 20, which is actually pretty easy. That would be in a lot of catalogs. All right, so we have the sample, it's wetted, it's inside a beaker, we're about to do the measurement. One thing we might do to help break up those agglomerates is just add energy. And we might put the samples in an ultrasonic bath, or maybe we'll hit it with an ultrasonic probe, where due to the wavefront, bubbles and cavitation adds energy, and that energy is used to just break up agglomerates. Very useful, but we also want to make sure we don't add so much energy that we start breaking particles, because the goal of the measurement is typically to measure the size distribution of the individual particles. So to look at how we might start putting some of this together, we'll look at a few case studies here, where we'll look at the effect of energy and the effect of dispersant in dispersing powders prior to or during a particle size measurement. And I had no trouble just getting on my laptop computer, which I carry around with me to do demos and measure at customers' locations. And here's a particular nasty powder where I measured in a liquid with no ultrasound. And that medium particle size looks like, what, maybe 600 microns. Then we used the powerful ultrasonic probe in the LE950. After 10 seconds, a big change. After 30 seconds, change some more. And after 60 seconds of ultrasound, we went from a median size being up here, near maybe 600 microns, to where maybe it's 6 microns. So this is a very dramatic case where it wetted fairly easily, but we needed the ultrasonic energy to disperse this mechanically down to the single particle state. But how much energy we use is very important, because we don't want to break individual particles. And in order to understand, am I dispersing a sample or breaking particles, sometimes what I can do is I'll just overplot taking measurements without ultrasound, and then maybe I'll add increments of 5 or 10 seconds of ultrasound. And I look over here on the large particle size, and as I start adding ultrasound, I see the largest particles start disappearing. Okay, that's probably dispersion. But then I look at the tail of fines, And I look down here carefully, and if all of a sudden after here, it turned out to be after 40 seconds of ultrasound, I start seeing new particles appearing that weren't there before, I get concerned that's breakage. So we probably would want to do a study of what is the optimum amount of ultrasound to get good dispersion without breaking particles. This is not a method development webinar tonight. If it were, or if you wish to see one, there's one on the website, and would actually talk about using the Method Expert software in the LA950, which automates these kinds of studies of rigorously at increments of ultrasound, look at the effect on results, and choose the optimum amount. But it is very important to use the optimum amount of ultrasound when dispersing powders and liquids. So now let's talk about the effect of dispersants. So titanium dioxide can be a little tricky to work with, but the LA950 does a great job, which is probably why most of the TiO2 manufacturers in the world use the LA950 to measure the particle size. This was just some work I did, I think, creating a web page or something else to help customers understand using the instrument. I used PhotoFlow as actually a surfactant that is typically used to wet and disperse titanium dioxide. What I did is I dispersed it in the surfactant, and then I did a measurement, and then I did another measurement, and I just was recirculating the sample, and what was happening was after 30 seconds and 60 and 120 seconds later, the particle size kept increasing. You'll see here the D50 went from 0.57 up to about 0.8 microns. So what's going on? The particles are re-agglomerating with time. So we can use a surfactant to wet the particles. We could use ultrasound to disperse the particles. I don't think I used ultrasound here. We could probably do even better dispersion if I'd used ultrasound. But here I was just looking at the effect of dispersant. So this is titanium dioxide dispersed in PhotoFlow and DI water. But what I did is then I did the measurement not in DI water, but using sodium hexametaphosphate. So I think I measured in like 0.01% sodium hexametaphosphate. Redid the set of experiments, but while I was doing this, I also measured the zeta potential of these dispersions on the SC100. And I think I decided this afternoon, oops, I did a whole talk without showing one of the instruments we make. So yes, there's the SC100. It measures particle size and zeta potential. Okay, that's the commercial part of the talk tonight. It's a wonderful instrument. But what I used it for this study was I measured the zeta potential of the sample just in DI water. That is the red result here. And I got a result of minus 11 millivolts. That's a pretty low zeta potential. Under 30 millivolts, we usually assume is an indication this is not a stable dispersion. Then I dispersed the sample in sodium hexametaphosphate, and here I see the zeta potential increase to minus 47 millivolts. That's above that general rule of thumb. It's over 30 millivolts of zeta potential. That implies this should be a more stable dispersion. And sure enough, when I did the measurement, after it was dispersed in sodium hexametaphosphate, what we see is after the same time delay on the measurements, I see nice stable results. And so this actually is much better for method development. Why? Because with method development, we need to have repeatable and reproducible results. And what if the operator puts the sample in and measures it today, but then this afternoon he gets a phone call on his cell phone, he or she, and it doesn't do the measurement till 30 seconds later? If you use DI water, you would get a different answer. If instead you dispersed it in sodium hexametaphosphate, if you lose a few seconds talking on your cell phone, that isn't going to change your results so much. So that is a smart idea. So this is the effect of using an admixture, using sodium hexametaphosphate, which improves dispersion in that the particles then don't tend to re-agglomerate. So in summary here, we talked about surfactants, the different kinds of surfactants, how one might choose a better surfactant for a sample, be careful with the concentration of surfactants. Admixtures, I talked about sodium hexametaphosphate. Sometimes we use sodium pyrophosphate. Sometimes we use this just in the beaker to disperse the sample. Sometimes, if it's a very difficult sample, the whole system is recirculated with water not just DI water, but a dilute water sodium hexametaphosphate solution. We use ultrasound to add energy to break up these agglomerates. There's a very powerful ultrasonic probe in the LE950, but sometimes the worse samples we use a more powerful external probe. That helps us break up those agglomerates, and then these other admixtures help keep them from re-agglomerating. So you do sometimes just go to your lab and tinker around and come up with the best way to disperse this powder in a liquid for doing the particle size measurements, but we're hoping that today we gave you a more methodical approach, a little more insight into what's happening with the chemistry and what some of your options are. And now when you take these next measurements with more difficult samples, you have a little more basis of how to approach this in a rigorous manner. So this and all kinds of other information will be posted on the website. Ian already said, this will be posted on the website where the other webinars are. For instance, if you wanted to hear the webinar on method development, you do have to go through the Download Center where you have to register once to do that. The previously recorded webinars are available here in the Download Center along with all of our application and technical notes. If you do need to just get in touch with us and you forget our email addresses, even though it was at the start of the presentation, you can just go here and send us questions. And what we started doing now and just recently is up here in this corner, we always show what is the next webinar. And I took this image today because you're listening to the current webinar. And I don't remember what the next one is. Do you remember, Ian, who gives the next webinar? We'll have to change this over soon.
What a nice segue. I'm actually giving the next I'll be giving the next webinar next Wednesday on the importance of particle size for Trona.
Can't miss that one. Look forward to it.
I'm looking forward to it. I hope other people are looking forward to it.
You should describe what Trona is. I bet not everyone knows.
Trona, well, the gist of the presentation is going to be that Trona is a very valuable substance for several applications, but particularly in the U.S. it's being used as a sorbent for power plant emissions. So if you wanted to sequester certain materials from going into the atmosphere, you might use Trona to do that. We hope you all have a good rest of the day and hope to see you again at the next webinar.
Okay, bye Ian, bye everybody.
Bye Mark.